Okay, so now we're going to prove there's an infinite number of conservation laws from this rather ingenious way, and you're going to go and calculate some of these yourself. Okay, I'm not going to give you actually any more than the two you've got. You're going to find the next ones. So we go to this modified KDV, which is written in this following form. Oops, I don't use V here. So it's a related equation, and it's related by this transformation u is equal to minus v squared plus dx of v. So this is actually a differential equation you've got to solve to try and find, so from this equation here you could map and find u that up to a constant, but we're not really interested in adding into constants here, right? So and we can see how this works really simply if we just to do some substitution here. So we start out with the KDV equation. And then we substitute that u is equal to that. And rearrange it. Okay, I'm not going to do that calculation. But what we get is we can write it as the following form. You can see how this is going to work if you just take all the bits and you could reassemble it. All right, so since this is 0, one of these two is going to be 0. So if V satisfies the modified, whoops, I've written U here instead of V. Let me just fix that up. If V satisfies this modified KDV, then this expression from this transformation U is going to satisfy the KDV, right? This is going to be equal to 0. You could also have some extra bit here coming from here, but it's just going to be a simple sort of linear part. All right, so now we've got to try and think about how to prove that there's an infinite number of conservation laws. We'll use this modified KDV, so they're basically the same equation, just transformed. So we generalize this here. So let's go through this. So we write U is equal to it's like a perturbation expansion in W. Okay, and these were very well known to people, sort of these power series and epsilon type solutions. So if we substitute that, so it's like the mirror transformation, it's some related transformation here, you can do the W squared, and it's got this parameter epsilon. If we substitute that into the KDV, there's a lot of algebra to come to this expression, but you end up with, we take the KDV, what we get is this expression here. I'll write it down below here. So we get 1 minus epsilon dx. It's 2 epsilon squared W times dt W plus 6 dx cubed W. Okay, equals 0. You can sort of imagine that's going to work. If I substitute that into here, I'm going to get the time derivative of W, so that's going to appear here times 1, and then I'm going to get all these other expressions, and you can imagine it can be factorised. It's going to be a bit of algebra to work that out, but you can follow along and you can get this expression here. So if this is equal to, if this thing here is equal to 0, then clearly u is equal to 0. So this is our equation here. So I'll write that down here. U satisfies the KdV provided that we have this equation here, dTW plus 6W minus epsilon squared W squared. Okay, whoops, I've forgotten a term here, haven't I? dxW. Plus dx cubed W equals 0. Okay, so this is a sort of a different, we haven't got very far here. We've got a very similar equation to the one we started out with. That was our original equation. This is our new equation. It's got this epsilon parameter. And then, so this is not leading us anywhere too clever, but we do this ingenious idea here where we write the solution as a power series. So W depends on x, t, and epsilon, and we write it as the sum of powers of W in powers of epsilon. And we're basically going to get into conservation law for each Wn. Okay, so I've just noticed here I've got a mistake. That of course should be a W here. Oops. Okay, so this equation here is in conservation form. So we can write it as d by dt of W plus d by dx of 3W squared minus, what is it going to be, 2 epsilon squared W cubed plus dx squared W. So we know that the integral from minus infinity to infinity of W is always equal to a constant. Okay, I've sort of run out of space here, but this is true for every epsilon. So it does it independently of epsilon. So we can set epsilon equal to 0 and we can get it for W1. And if it's true for all epsilon, so again I've made a mistake here, that should be to the power of n. If we do this for every epsilon, since it's true for every epsilon, it must be true that it's true for all Wn. So we get minus infinity to infinity, because it's true for every value of epsilon. You can sort of just think about, if I could take epsilon equals 0, that gives you 1. And then epsilon, you can take the derivative and work out the next one, etc. Okay? You get a contradiction if it wasn't true. So this thing here must be equal to a constant. It must be true for every value. Just the key point is that it's true for all epsilon, independent of the value of epsilon. Okay, so basically there are conservation laws written down. We've worked it out. So all we've got to do now is work out what those conservation laws are, back to the U. And we've got this expression for U up here. So maybe if I just do a bit of rubbing out here, get rid of all this, and just keep that up here. It's kind of like a lot of genius ideas, the argument's not super complicated. Okay, it's a bit of algebra to write it in that expression. I've never done that. But, oops. See if I can put that back. Whoops, I can't. Okay, don't do that. Okay, so I'll just fix this back up. All right, so we've got this amazing thing. We've sort of proven that this W is given by the sum of epsilon to the n Wn, and we know that the integral from minus infinity to infinity of Wn dx is a constant. So all we've got to do is we've got to just start to work out, by substituting in this thing here, we've got to work out what Wn are. These are the unknown. So we basically substitute in here this expression, and and we get u is equal to the sum of epsilon to the n wn minus epsilon times the sum of epsilon to the n dx w minus, and then this is a bit tricky, it's epsilon squared. This is the nonlinear part. And then we try and pull out the powers of epsilon. Just find the powers of epsilon. So how do we do that? Well, let's just start here. So we go epsilon to the power of 0, that's going to be easy, right? So we get epsilon to the power of 0, so we get u is equal to, the first thing here is epsilon to the 0 is w naught, and then this depends on epsilon, this depends on epsilon squared, so u is equal to w naught. So the integral of u is equal to 0, it doesn't tell us a lot. Then we go to the power, epsilon to the power of 1. And we just try and think about where you get epsilon to the power of 1. We have 0 here, must be equal to, we have w1, and then we've got minus epsilon times the derivative of w0. Okay, so w1 is the x derivative of w0. There's no, the other term here I should say has epsilon squared in the front, so there's no epsilons, right? So that means that w1 is the x derivative of u. So the integral of the x derivative of u is also conserved. That doesn't actually tell us anything because we already knew that the integral of u is conserved and the integral of the x derivative of u is conserved. So the odd conservation laws are just the previous law with the derivative. Okay, I'll just maybe just write the conclusion to that here. Whoops, don't do that. Just in purple here. So w1 is the x derivative of w0, which is the x derivative of u. So that x derivative of u is conserved. But that doesn't tell us anything, we actually already knew that. And then we go to the epsilon to the power of 2. So we're going to get 0 equals, always get w2. And then this one here is going to be easy as well. It's going to be minus the x derivative of w1. And then we finally get an epsilon squared, and we get epsilon squared times epsilon to the power of 0 times w to the power of 0. The only place it appears there is minus w0 squared. This thing here is maybe the trickiest one to expand. Maybe it's useful if I just write those out somehow here, right? So this is going to be equal to w0 plus epsilon w1 plus dot dot dot. And then you're going to be minus, and this is going to be epsilon times the x derivative of w naught plus epsilon squared times the x derivative of w1 plus dot dot dot. And then over here we're going to have minus epsilon squared, and then we've got to think about this one. We've got w naught squared plus epsilon times, and there's going to be 2 w1 times w naught plus, and then it gets a bit tricky, right? Dot dot dot. To work it all out, you're going to have the epsilon squared is going to be w1 squared w naught times w2, etc. Okay, you're going to be a few more terms coming in here. Okay, and that's something to work out for the assignment. All right, so coming back to this, there's the expression there, so that's equal to 0. So that tells us that w2 must be equal to w naught, which is u squared, minus the x derivative of u. Sorry, whoops, what have I done wrong here? The x w2 is w naught squared plus the x derivative of w1, and w1 is u, so is the x derivative of u, so it's d squared u. Okay, so that's the epsilon cubed conservation law. So that tells us the one that we saw. We know that this thing here doesn't add anything to it because we already know u is conserved, so therefore the x derivative of u will be conserved as well. So this is telling us that the new part is this u squared part. All right, and then you can carry on. And then and the notes does epsilon to the power of 4. Okay, it doesn't add a lot to it. It gives you w3 is equal to dx cubed u plus 4u dx u. Okay, and then the next one, this isn't new, this is just related to the other one, a derivative of it. In some way, the epsilon to the 5 is the new one, and that's the one you've got to work out yourself. All right, I'm finishing there.